So we're going to start getting into some of the chapter 6 materials. These are really quite important. We're starting to get into a little bit of the stress strain behavior and what happens, why it happens, what's the molecular level contribution to this. It's just sort of all of these things. We need to be able to see what's going on there. Okay, having said that, there are, stress and strain, elastic behavior, when you load something, how much deformation occurs, what material's going to deform the least, all of that sort of thing. At what point does permanent deformation occur, all of that detail. What details or what materials are most resistant to permanent deformation, and then toughness and ductility. What are they and how do we measure them? This is a lot of stuff all in one chapter. I'm going to attempt to make sure as we go through this to explain how all of this works and bring in some real examples. So the other week we were starting to work on some examples where we looked at some examples where magnesium, this British chap is trying to figure out whether or not he can forge magnesium. And the answer is no, you really can't. You learned why in terms of the crystalline lattice structures, why that doesn't work that way, why it always shears on a diagonal, always. It's because of the crystalline lattice orientation, the way that magnesium crystallizes, it's always going to shear on that diagonal. So you can cast magnesium carefully, very carefully. You can cast magnesium. Trying to forge magnesium, not going to happen. You could probably flow form magnesium, actually, which is a hybridized process. It's a casting under pressure, essentially. So you get some forged-like behaviors and some not forged-like behaviors. Okay. The deformation that he's normally doing in steel when it's being forged, and I'll pull up an example of what the deformation looks like, is he is often doing plastic deformation always in what he's doing, but there is some element of elastic deformation always when you are doing deformation of an alloy. Okay, what does all that gibberish mean? You start out with the initial stack of atoms here on the left. What then happens is you start applying an external force. That force in this case is in tension, so it's trying to pull this thing apart. Okay, makes sense. When that's happening, we have a couple things that need to be taken into account there. One of which is the bonds start stretching, so they get a little bit weaker between the layers, and there's a sigma, a change in length in the material. This is really important. So here we've got that bond starting to stretch. We have this change in length sigma, and what that does is gives us a linear region of elasticity, meaning that it is reversible. What that then means is you have, when you take that force away, you have a return to the initial structure. So the unloaded case looks like the loaded case. So we start out with the force graph, and we come up and then back down the same line because it's reversible. So we go up as we stretch, and then we come back down as we return to the initial state. So we stretch and then shrink by that same sigma, that same amount, that same change in length. So it's a change in length with respect to a change in length that we'll learn about later. There is also a non-elastic behavior, and a non-elastic looks like this, where we have a change in length that is not completely reversible. So it doesn't follow the linear path. So springs have a very wide reversible region, and they can bend and come back multiple times without fatiguing because of the arrangement that they are formed in. Also has to do with the exact specific carbon content. There's some other factors in there as well. Plastic deformation. This is the form that you're perhaps more familiar with. This happens in all sorts of materials, especially like if you're bending the tabs back and forth on a soda can. Probably everybody has done that at some point in time, and it pops off. Then that gives you the ability to change the form of the metal. And what you're doing is by adding a load, you have the elastic plus the plastic deformation. And this gives you a slip along these diagonal planes. And this is exactly what was happening as he was forging that magnesium, for instance, is that was creating conditions where you are causing slip along those planes. Those planes are shearing, so you're moving a defect along those planes relative to each other, and they slip. So as you're adding force, these bonds become weaker and weaker between these layers, and they're able to slip, and that causes stretch in the metal. Plastic is a permanent deformation. So when you unload it, you now have a misalignment of these planes. So the planes are still sheared with respect to each other, but it goes back to a state where it looks very much like the initial state, except now we have sheared planes. And this change in length, after it relaxes, what's left is called the plastic deformation. So this begins the first part of what we know as the stress strain curve. So you have a linear elastic region, then you have a plastic deformation region, then the linear elastic recovery happens, and you recover this portion that was elastic deformation, but you're left permanently with this change in length, which is the plastic deformation. And this is why, as you keep fatiguing the metal, the aluminum pop can eventually gives up its tab, because you go back and forth, you keep stretching and shearing these planes, and stretching and shearing and stretching and shearing. Eventually it gets so thin it can't hold on anymore, and the smallest application of force causes it to fall off. You probably had no idea you were being so mean to so many planes of atoms. Shame on you. The tensile stress is what this is referred to. Tensile meaning we put it in tension. This is pulling something apart. The tension is causing the same force to be applied to the top and the bottom. So FT here is meant to indicate the tensile force as we put it in tension. The area over which that happens is often referred to as A0. It's the cross-sectional area before the loading. It's very important to remember that this is the cross-sectional area before the loading. Anybody in the comments want to take a guess as to why? Why is this so important that that be the cross-sectional area before loading? It has to do with the deformation. What has to happen to the area? If we add stress and it has to change length, What has to happen to the area? Because we can't create or destroy matter, as much as politicians might promise otherwise. So what has to change? The area has to change. So the area gets smaller and you have a stress that's created. This is an example of what's called shear stress. So this is adding shear stress into the mix and giving you a net force. So the force in shear, meaning trying to rip apart those molecular layers within a plane. It's trying to rip those planes apart from each other. The original cross section before loading is this A0. As these forces are applied, the areas change. So as you begin to shear something and as it begins to move, you reduce the total area that it's shearing across. The shearing force is the same. The area decreases, meaning the overall stress goes up. Same thing here. As that area decreases, the force of tension stays the same. So the overall stress has to increase to keep it balanced. So the area shrinks, the stress increases, and this is what happens. So in the examples of tension cables, those are probably the easiest example to reference. These simple tension cables are force applying in both directions across area. As that cable is loaded, those fibers that those cables are made of are pulled in tension, and the overall cross-sectional area of the cable reduces when it's in tension. So you have the simple tension stress in both directions, so tensile stress in both directions. That's always going to be denoted by sigma here. Or this one, yeah, this one's always going to be denoted by our sigma. So we also have torsion, which is yet another aspect of force. And in this is trying to introduce the concepts at a very high level, not yet trying to apply these to specific problems, but just understanding the different kinds that are happening. The drive shaft that is maintaining the tension on the cable is under torsional stress. So it's a form of shear stress. It's not a linear shear. It is a rotational form of shear, which makes sense. You really can't have a rotational form of tension. Not really. It's most of the time it's going to be simple tension that we're modeling. Torsion, however, is that twisting force where a drive motor is trying to twist one end and a load at the other end is trying to resist being twisted. So you have a rotating, counter-rotating M, which is a moment. So the moment is the same units as a torque, and that's really kind of the best way to think about this is if you grab onto the end of a wrench and you pull it, or the end of a lever or something, and you pull it, you are applying a moment to that lever. That is also applying a moment, and there is therefore a counteracting moment on the other end of the thing that you're rotating, whether it's a switch, whether it's something more extreme, if it's a winch on the front of a truck or the back of a tow truck or whatever the case is. You have a moment and you have a counter rotation moment that's trying to make things happen here. So there's a couple instances where this can be done and make sense. So I've got something tearing itself apart here. I'm going to have to stop. So the torsion is an example of what this moment and counter rotating moment are doing. So you have a shear force across this small area block, and you have this area, you have shear force basically in all of these different regards. They're showing you it in sort of all around. You're just looking at the top area. This makes a little bit more sense. So you have a shear stress, you have a counter shear stress going the opposite direction, so that those two are in balance until the material starts yielding, and then you have some differences in the way that these are working. Couple people having connection issues. So we have a couple pieces of the puzzle here going on. So you have a shear force divided by area is your torsion. This is the same as the moment divided by the area of the circle. So this is a circular area times the radius. That's because the moment is in the same units of a torque, so it's a force times a distance divided by that distance. That force divided by the area gives us the shear, because these are important dimensions to maintain. So it's in the units of pressure, right? So it's force divided by area. So you can think of it as a mechanical pressure. It's a mathematical reality that it behaves as a pressure. And that's why it does what it needs to. So the example of simple compression is something large with a smaller area, and you have a force being concentrated in this area. So this is under compressive stress. So it's the same idea as tension, just going the opposite direction. So the Canyon Bridge, this is one that I happen to have personally been across a number of times, including when it was -4 before the wind chill that morning. And then all of the pansies sent an email at 9 a.m. saying, hey, actually, we're going to be closed because the bridge is iced over, and so you probably shouldn't come into work. Too late, I had already been there for about 3 hours. So, oh well. So yeah, very strong bridge, an arch bridge design, simple, minimal materials, really entertaining when protesters are walking across and carrying really big signs and doing like the whole marching, walking person puppet thing. Doesn't make any sense, but I guess protesters don't have to. So is what it is. These are examples of things that are under compressive stress. And this particular example is that member probably actually is under compressive stress. These aren't all necessarily under compressive stress, and we'll learn why later. But there's a lot of pieces to this puzzle. Tank pressure is another example of this. So any kind of pressure in a pressure vessel is going to give you tension stresses. So there's not compressive stress inside like you might think, but there is a biaxial tension. So you have tension in one direction, and if you were to take one small element out of the skin here, what they're showing is if you were to take one small square differential element out of the skin of this tank, you have a circumference, which is this one. So you have a circumference around the tank where you have stress, and it's pulling it apart in both directions. And you have the tension across Z, the Z axis, that is trying to push the end tanks off. So we'll look at some of the math involved as to why and how those are different. The circumferential is often a higher stress actually than the end tank is, but this is the reason why they fail like they do. Something like a fish underwater, however, has these stresses in all these different axes. So why does it have those? Why are they behaving this way? Why are they doing the things that they're doing? They have compressive stresses. So if you were to suddenly put a fish into a vacuum environment because its structure is designed to be pressurized on the exterior, if you reduced that local pressure, you would create a scenario where the fish would just explode. The system is not designed to be able to handle a lack of pressure on the outside. So if you were to put them in a vacuum, they would pop up and explode and make a greasy mess on the inside of your vacuum chamber. Why you would want to do that, maybe you're actually just Sid from Toy Story, I don't know. But the design criteria for the fish are they operate in an environment where they are constantly under compressive stress from all axes. So it's always a positive compressive stress. So then there is strain. Strain is the result of what stress does to the material. So let me see if I can find an example. Let's see if I can find a good example. Let's see. Let me see if there's some good examples. There's a couple of them. So there was a recent example, because I think there's some instances where we think we have mastered pressure vessels and things, and nothing bad ever happens anymore or anything like that. So this is a great example to show you. Get it here. This is a thing that happened. I'm going to go ahead and share this because I think this will help to get you guys some of the important detail that you need.
April 3rd, 2017. The Loy Lang Box Company of St. Louis, Missouri. One worker and 3 members of the public were fatally injured when a pressure vessel catastrophically failed, causing an explosion that launched the pressure vessel into a neighboring building. The Chemical Safety Board investigated and found that over the course of many years, an area of the failed pressure vessel had thinned due to a known corrosion mechanism that was poorly controlled at the facility. And the CSB found that Loy Lang repeatedly ignored clear warnings that corrosion was causing major problems within its operations. In fact, prior to its failure, Loy Lang ran the pressure vessel normally, despite knowing that it was leaking. It was a safety emergency that unfolded in plain sight.
The incident at Loy Lang resulted from a tragic series of circumstances: ineffective corrosion management, inadequate pressure vessel repair, a lack of inspections, and the absence of sound safety management systems. The result of those factors was that a severely corroded pressure vessel, which presented a serious safety hazard, was allowed to operate until it ultimately failed, resulting in the death of 4 people.
Loy Lang manufactured corrugated cardboard, which is used to make other products such as boxes and retail displays. Part of the process to make corrugated cardboard involved heating paper using a steam generation system. The steam generation system used municipal water. The water was fed into a vessel called the makeup tank. There, the water was treated with chemicals and heated to approximately 200 degrees Fahrenheit to remove dissolved gases, including oxygen. This was necessary because oxygenated water is corrosive to steel equipment. The water then flowed from the makeup tank into a larger pressure vessel called the semi-closed receiver, or SCR. The SCR was comprised of a cylindrical center and 2 end pieces called heads. All 3 sections of the SCR were made of steel and susceptible to oxygen corrosion. The SCR was kept under pressure so that the water inside would retain more heat than it could at atmospheric pressure. From the SCR, the water was pumped to a generator that converted it to steam, which was used to heat the paper. The steam then cooled, condensed back into water, and flowed again into the SCR. At the end of the workday, Loy Lang operators shut down the steam generation system, leaving the SCR filled with warm water. At the beginning of the next workday, operators would restart the steam generation system. During the daily startup, operators would initially block the flow of water into the SCR from both the makeup tank and from the condensed steam returning from the corrugation process. At the same time, the water remaining in the SCR from the previous workday was pumped to the steam generator. As a result, the water level inside the SCR would drop from its normal height of about 14 feet to about 2 feet. When the SCR was nearly empty, operators would then allow water to flow into it from the makeup tank. Loy Lang's steam system was used to heat the water in the makeup tank. But at this point in the startup process, the water in the makeup tank may not have been effectively heated to approximately 200 degrees. So not all of the dissolved oxygen in the water was removed. Therefore, during startup, oxygenated water entered the SCR instead of the heated oxygen-free water used during normal operation. This presented a serious corrosion hazard within the steel vessel. Eventually, hot condensed steam returning from the corrugation process was available, and operators opened a valve to allow it to flow into the SCR, reducing demand for water from the makeup tank. But due to the design of the SCR, water did not flow easily through the bottom head. Operators could achieve flow in the bottom head by opening a manual valve and allowing water to drain from the SCR, a procedure known as a blowdown. But between blowdowns, a small volume of oxygenated water would remain trapped in the bottom head, and over time, the oxygenated water corroded the steel. The potential for corrosion was a known problem. During its time operating the SCR, Loy Lang experienced at least 3 leaks due to corrosion. In response to a 2012 leak, a repair company removed most of the bottom head. The company patched it with new steel. leaving the remainder of the bottom head in place. But the original steel of the bottom head that was left in place was also thinned from corrosion. And between 2012 and 2017, it continued to degrade and eventually started to leak. On Friday, March 31st, Loy Lang operators noticed a leak that appeared to be coming from underneath the SCR. A local welding company was contacted to assess the SCR, but was not available until the following Monday, April 3rd. Loy Lang continued operating the leaking pressure vessel throughout the remainder of the day on Friday and shut down the steam generation system as normal that evening. On Monday, a Loy Lang operator began the regular startup process around 6 a.m. At approximately 7:20 a.m., the vessel catastrophically failed. When suddenly exposed to atmospheric pressure, the water in the vessel flashed into steam, greatly expanding in volume. The result was a boiling liquid expanding vapor explosion, or BLEVE. The explosion launched the SCR from the Loy Lang building and into the air. It traveled 520 feet, crashing through the roof of a nearby business a block away. Other debris damaged a third building as well as a parked vehicle. One Loy Lang operator and 3 employees of the nearby business were fatally injured. During its investigation, the CSB found 4 safety issues contributed to the explosion at Loy Lang: uncontrolled pressure vessel corrosion, ineffective pressure vessel repair, gaps in pressure vessel inspection and regulation, and deficient process safety management systems. The first safety issue is pressure vessel corrosion. Oxygenated water in steam generation systems causes corrosion in steel and must be managed and controlled. But at Loy Lang, there was a history of equipment failures caused by oxygen corrosion in the steam system, and 3 documented leaks in the SCR, including the 2012 leak that led to the repair of a portion of the bottom head. 5 documented corrosion failures in other areas of the system, and numerous undocumented leaks in the makeup tank, enough for the company to replace the carbon steel tank with one made from stainless steel to attempt to address the issues.
We found that all of the corrosion failures occurred in components of Loy Lang's steam system that, when operated under normal design conditions, should have experienced minimal or no corrosion at all. This points to the fact that oxygen was not properly managed or controlled within the steam system.
For instance, the CSB found that Loy Lang steam system water routinely lacked sufficient concentration of chemicals called oxygen scavengers that are used to remove oxygen from the water. And Loy Lang startup practices likely introduced oxygenated water into the SCR daily. The result was that over time, uncontrolled oxygen caused corrosion that thinned portions of the bottom head of the SCR so much that the vessel catastrophically failed.
Loy Lang needed to adequately remove oxygen from its steam system water to prevent corrosion. But despite evidence of the hazard at the facility, the company did not take effective action before it was too late.
The second safety issue found by the CSB is pressure vessel repair. In 2012, the repair made to the bottom head of the SCR left a corroded steel ring in the vessel. The ring continued to corrode for 5 years until it failed on the day of the incident. The CSB found that this repair did not comply with regulatory code. The regulatory body with authority at Loy Lang is the City of St. Louis. The City of St. Louis Mechanical Code required repairs of pressure vessels to conform to code from the National Board of Boiler and Pressure Vessel Inspectors. The 2012 repair of the SCR was performed by a National Board R-Stamp holding company, which meant the company was authorized to perform repairs to pressure vessels in accordance with the National Board Inspection Code. But the CSB found that the repair did not adhere to that code, which generally requires that all defective material be removed. As a result, the 2012 SCR leak repair was ineffective, incomplete, and dangerous, and it was the unacceptably thin remaining material from that repair that failed, initiating the incident. At the time of the 2012 repair, National Board Code required the involvement of a repair inspector, but did not require specific inspection points during the repair process to provide quality assurance. Instead, the level of scrutiny applied to any repair was left to the individual inspector's discretion. In this case, the repair inspector approved the repair plan without first evaluating the SCR, and the inspector did not personally witness the inappropriate repair to the SCR bottom head. Had the repair inspector seen the repair in progress, the inspector might have detected and refused to accept the inappropriate repair, which could have prevented the incident. Since the 2012 repair, the National Board made significant changes to the code, requiring inspectors to designate inspection points throughout the repair process. But gaps still exist. For example, the code does not specify whether the repair inspector must make in-person contact or view the job prior to reviewing and accepting a repair plan.
Understanding the extent of damage to a vessel is a critical step for a repair inspector to make when determining whether a company's repair plan is acceptable. We believe that this step should be specified in the National Board Code.
As a result, the CSB made a recommendation to the National Board of Boiler and Pressure Vessel Inspectors to update their rules to include prescriptive elements in the inspection process that would prevent the acceptance of a non-conforming repair or alteration. A third safety issue found by the CSB is pressure vessel inspection and regulation. At the time of the incident, the St. Louis City Code required an annual inspection of boilers and pressure vessels by city inspectors. But during the lifespan of the SCR, Loy Lang never applied for an installation or repair permit, or otherwise registered the vessel with the city. Therefore, the city had no knowledge of the SCR and no means of proactively initiating an inspection. The CSB found that despite the regulatory requirement that the SCR undergo annual inspections, there was no record of a city inspector ever having inspected the pressure vessel. Furthermore, the city had not inspected the Loy Lang steam generators generally since 2010.
Unfortunately, the city of St. Louis missed opportunities to prevent this incident. Had the city performed more regular inspections of the Loy Lang steam system, it could have identified the unregistered SCR, sealed it from operation, and ensured its inspection, potentially catching the corrosion hazard before the vessel failed.
At the time of the incident, despite requiring an annual inspection by city inspectors, the city code offered no specific guidance on inspection methods or tasks beyond the annual frequency. The inspections were specified to be as thorough as circumstances permit. The city of St. Louis has since changed its inspection requirements to require that boiler and pressure vessel inspections be performed by an approved third-party agency rather than city inspectors. However, the city still has not adopted any specific inspection methods or tasks beyond the annual frequency, and neither city inspectors nor third-party inspectors are explicitly required to hold any inspection certifications, except in the case of certain boilers. As a result, the CSB recommended that the City of St. Louis Board of Aldermen revise the City of St. Louis Mechanical Code to adopt a national consensus standard, such as National Board Inspection Code Part 2, to govern the requirements for in-service inspection of boilers and pressure vessels, and revise the city's mechanical code to require pressure vessel inspections to be performed by a National Board of Boiler and Pressure Vessel Inspectors in-service commissioned inspector. Finally, the fourth safety issue the CSB found at Loy Lang was the lack of an effective safety management system.
To prevent this incident, Loy Lang needed to understand the hazards of its operation, implement and maintain safeguards to prevent corrosion in its steam system, and monitor those safeguards to ensure their proper function.
The CSB found that Loy Lang's management did not understand the hazards of its operation and did not see a leaking pressure vessel as a safety emergency. The company failed to prevent corrosion in the SCR, had no inspection program, never investigated or addressed the root cause of the corrosion in its steam system, and repeatedly operated the SCR while it was leaking, including on the morning of the explosion. Therefore, the CSB concluded that Loy Lang did not employ sound safety management principles in addressing the risks associated with corrosion in its steam system.
Had Loy Lang instituted elements of an effective safety management system, including mechanical integrity, incident investigation, and effective corrosion prevention programs, the hazard of corrosion could have been mitigated and this incident could have been prevented.
As a result, the CSB made a recommendation to the Loy Lang Box Company to develop and implement a comprehensive safety management system that includes elements recommended in industry good practice guidance publications.
Leaking pressure vessels can be dangerous and should be thoroughly evaluated to ensure that they are fit to operate. But even before a pressure vessel is compromised, there are many ways for companies to ensure that damage mechanisms, including corrosion, are properly understood and controlled. Doing so can prevent catastrophic incidents before they ever happen. Thank you for watching this CSB safety video.
So on the one hand, it might seem like that's a waste of time and why are we going over that? But what I need you guys to actually understand is that this is serious stuff. That was in 2017, okay? This was not 150 years ago. This was something that was an actual incident where people did not go home to their families or even to the hospital. They just went straight to the morgue because of not understanding what was happening with the materials. When you put them under stress and you combine all of the stuff that we're teaching you this semester, you are going to know enough to, if you actually see a situation like that in a workplace, that's one of the few instances where see something, say something should actually apply, instead of being some ridiculous way to spy on your neighbor because you don't have enough to do with your life or something. You should actually pay attention. If you have a pressure vessel that's leaking, turns out that's really, really, really bad. And I want you guys to comment on where you noticed that failure happened. Where did the material come apart? If you guys didn't catch it, I'll have to bring the video back to that portion. Let me see if I can find it. See if you guys caught it. So it was right at the weld seam, exactly. We're going to learn later about heat affected zones, and that's exactly what happened. The heat affected zone is what is immediately adjacent to the weld. And if we look back at that for just a minute, where it failed specifically is literally right at the outside edge of this weld. This is typically how these are going to fail. So when the repair was done, they established the repair point as the point of failure, and no welding company that has any kind of integrity would weld good new steel to thinned corroded steel in a pressure vessel. The professional welders that I know would absolutely throw a fit and say, no, you have to completely replace the entire base of this, and it's going to be much more expensive because we have to remake all of that curvature. So instead of being lazy and cutting corners, All of the welders I know would have taken issue with that, but it thinned to such a high degree that it looks like here the repair piece is 1/4 inch thick and the piece that they welded it to is less than 1/8 of an inch thick because of that corrosion. That's really bad. That's really bad. So these are actually important parameters. We're not teaching you this because it's stuff you'll never need to know. In fact, quite the opposite. It's stuff that you're going to need to know so that you can actually stay alive at your job site, because it turns out it's a little bit more fun if you arrive alive at the end of a day of work. So what that stress did to that application, still having connection related issues. Okay. What that stress did to the material is it created strain. Strain is the actual movement of material, the change in dimensions, and it's usually using epsilon, which is a little different character here. It sometimes comes across in the slides as E, but it's actually epsilon, lowercase. The strain is the change in width. It's this length. So you see at the top and the base, you have half of the delta. You have half the delta. So half that thickness, both top and bottom. Half that delta. So this is lowercase delta. The sigma is the stress symbol that we've been using. So that's lowercase sigma. Just to be clear, the strain is the change in length with respect to its original length. So that delta divided by the original length, L naught, is the actual strain in tension. There's also a lateral strain component. So that is the minus delta in L, and half of that is experienced on either side of the material. Assuming it's an isotropic material instead of an anisotropic material. Again, we'll go more into depth later with anisotropy and so on. There are reasons we need these. So shear strain is a little bit different. Shear strain is something that that creates a shift in the orientation of these individual squares or really cubes of material. So there is a delta X that happens, and because of that, the Y stays the same height, but the shear is being applied in the X plane, and so you have a movement of the top relative to the bottom. That movement is what's called shear, and that change in angle theta is described by the change in X, the delta X. This is capital delta for those of you that haven't studied Greek, which is probably most of you. Capital delta X. So this is a large change. Lowercase is meant to be smaller change. Still both delta used to look at the difference between 2 points. So the large change in X divided by Y, that ratio is proportional to the tangent of theta, the angle, and that angle becomes less than 90 degrees by whatever that theta is. Strain is always dimensionless, so that we have an idea, independent of the scale of the object, how much it's moving. This becomes important for a lot of the calculations and things that we're doing, but it's important to remember that this is meters divided by meters, inches divided by inches, whatever it is, it's meant to be unitless. So long as you're using consistent units to calculate it, it should be the same, meters over meters, inches over inches. That's the whole idea, is to make it a dimensionless parameter so that regardless of what unit system Mars lander, it's an incident that happened at this point, probably before some of you guys were even born. Dimension screw up at NASA caused a crash of a probe into the surface of Mars because somebody did something and they didn't communicate that they had already converted it to centimeters, and they put it back to inches. And so dimensions were wrong. It didn't deploy properly and just became a smoking hole in the Martian surface. It was really embarrassing. So I don't want to TV one day and know that, hey, that was one of the engineers I knew. I taught that engineer. That'd be really bad. Yeah, that well, NASA has had some mistakes prior. However, they no longer do space exploration. They're all about climate change now, thanks to the Obama administration and all of the great things that we have left over from that. So the testing that we're going to be doing is similar to this. We may or may not get to use the extensometer. Yeah, we may or may not get to, but the tensile testing machine looks a lot like this. There's a reason why we use it this way. What it's designed to do is take a load cell measurement, meaning a force measuring cell. The extensometer is mounted to the specimen, usually clamped on. So there's the possibility of the extensometer slipping and creating some aberrant reading, stuff that you have to account for in your measurements. Then you have a moving crosshead because it goes between the threaded portions so that this portion stays fixed while the bottom portion moves. These two are, I think here, they're shown as counter rotating, which would actually be bad. So their diagram should actually be like this, because if they're both right pitch threads, as these are, you need them both moving in the same direction. Otherwise, the crosshead would go down here and up here, and then you would have a very expensive, very broken machine. So we're going to go ahead and say they go the same direction, because otherwise that won't make sense. But what this does is, as the crosshead moves down, so you have these co-rotating axes, as the crosshead moves down, it applies force to either end of that specimen. The load cell is measuring how far that goes. And then the specimen will have what's called a gauge length, which is you have the top and bottom of the specimen. Sometimes these are threaded. Often that's not really actually threaded into the holders. There's some kind of clamp that holds onto the threads. So they're not actually usually screwed into place. They're just held in place by some clamps. The reduced section is important. Let's see in the comments, why would you have a larger diameter where you're holding it and a smaller diameter, or a larger area at the top and the bottom and a smaller area in the center? Why would we want to do that for this? That's referred to as a dog bone test. Why would we want to do a dog bone test with that? What change happens And why would that be important? Because shouldn't we change, like, have it all be the same diameter all the way through? Like, why are we changing the dimensions? Isn't that like altering your test result? Why would we do that? Let's see what the answers come in as. Why would we want a thinned or reduced section? Yeah, so it's all about controlling where the force gets concentrated, because what that does is limit and constrain where it can actually break, which turns out to be a pretty important parameter. Okay. So we've got, yeah, this is probably about the last concept that we can actually hit today. The modulus of elasticity. So this is also known as Young's modulus. The modulus of elasticity, capital E, is the slope of that linear region. We're going to spend some time on some different examples of some curves. I think I'm going to bring in a bunch of additional materials and their stress strain curves so that we can see what the behavior looks like before you guys go to do those tests. So the modulus of elasticity is the slope of Hooke's law, essentially. So Hooke's law, you guys have experienced in a different form. You've seen Hooke's law in this form, or are going to see it if that experiment is still in the 162 lab, force equals minus kx. So this is of the same form, referring to linear elastic regions. Hooke's law is applied to springs. This is where it's ultimately derived from. This principle that stress is equal to the modulus of elasticity, or Young's modulus, times epsilon. So again, our correct Greek character there, epsilon. So epsilon does this is our fundamental stress strain graph. So instead of x and y, we have stress and strain. So this is movement relative to the original length. This is the stress applied. So the force force divided by the area. That tension force, what that's doing is stressing that material out, and that that tension is reducing the effective diameter, or the cross-sectional area. So if it's a rectangular dog bone like we'll be testing, it does a similar proportional reduction in both the x and the y as it expands. In the z, so in the other axis, it's expanding, it's contracting in the other two axes. And it's always proportional unless, again, the material is largely anisotropic, and that creates some other issues. So F equals minus kx gives us the reference point that we need. So E is the rise over run, meaning that it is the ratio. It is the ratio of sigma over epsilon. So stress over strain, rise over run, very simple, only applicable in this linear elastic region. As soon as that curve starts to change and you get beyond the into the plastic, this no longer applies. So that's what you want to pay attention to, is this is only applicable in the linear elastic region, because it can't apply out here where the material is stretching, because Hooke's law has some base assumptions saying that these things are proportional. Otherwise, you'd have to add in all kinds of adjusting constants. You couldn't account for the nonlinear behavior here because this law has too many simplifying assumptions. So we'll leave that there for the moment. I know there's at least going to be a few questions, so I'm going to stop because I know there's also some examples of, I know there's going to be some questions. Again, I won't be able to answer anything relative to the test and scores and averages and all those things. But what other questions are there, since we're about out of time for today?